Alright, so now we're going to do something new with inequalities. And you've seen it already if you were watching the last video. It says if someone says, and we have this little slash between it simply means is equivalent to. And so what do you think what's going to happen to this statement? So this is the negation of our inequality. And our inequality is going to flip. So it's going to say it's equivalent to x going to be greater than or equal to 2. And so everything flips. It's kind of a phenomenon in a sense. And so anytime you see something like this happen, and so I'm just going to put an arrow right here so you can see it. It's just, this arrow means it's equivalent to, so it doesn't mean that, but I'm just saying that because I don't want to write it out. Alright? So x is greater than, x is not greater than or equal to 2. And so we're going to flip it, right? And so I'm going to give you 2 more. And I want you to try to do it yourself. Feel free to. And if not, then we're going to carry on right now. And so we're going to put these arrows and see what happens. And that gives us what? The opposite of that. And it's going to give us the opposite of that. It's pretty simple. Now we're going to move on to using De Morgan's law for inequalities. So let's do it. Here we have De Morgan's law. And it says use De Morgan's law to write the negation of -1 less than x and less than or equal to 4. And so this is going to bring in the ideas of we did in the other couple videos ago. And that was to break this down into its most simplest components / statement variables, right? And that's why we learned it, right? Because this is just a statement, right? P stands for this, let's say right here, and we're gonna have Q stand for this. It means the same thing. I mean, you can't see that P, that means P, and this means Q. So keep that in mind. That's what we did right now. So that just means P and Q. P and Q. So I'll put it here. That's just equivalent to, remember when we learned the logical equivalency? That's logically equivalent to this same statement. So we use logical equivalence mostly just for statements. So that's why this symbol is for, okay? Don't get it confused for being an equal sign or something. Equivalence and equal are pretty similar. But let's carry on to the problem right here. So we have negate, right, because we're going to do De Morgan's law. So this is our P and Q. And you remember what we got to do with our P and Q? We got to negate the P and Q. And so we're going to have this right here. Our next step is to negate this statement. And so what happens when we negate our statement? That is logically equivalent to saying negation P or negation Q. So there you no parentheses here. And so what happens? It's going to be the negation of this. So it's going to say -1 is not x, because that's just the negation of P, right? If it's -1 less than x, then it's going to be -1 is not less than x. And so what happens is going to be or, right, because we flipped it. And then it's going to say x is less than or equal to 4. So this is when we bring in the next idea we just learned right now. What is equivalent to? We flip these, right? That becomes -1 greater than or equal to x. This stays as or. And we flip this because this is logically equivalent to x greater than 4. So what does that mean for us? So I'm going to draw a number line. We're going to plot some points on there. So we're going to have a point right here that's going to be 0. And we're just going to do what we normally do with the number line, right? This is going to be -1. It's going to be 1, 2, 3, and 4. And so there's going to be a portion that's going to be a closed circle. And then we're going to have a portion right here that's going to be an open circle, right? So we got a closed circle over there. So I'll draw a little bigger. And then we have an open circle. So what does this say? It says -1 is less than or equal to x. And it's going to be going that way. So we're taking it all the way back to like grade school stuff. This says x is greater than or 4. So open, because when it gets there it's going to be 3.999, right? And we learned that in calculus. Alright, anyways, this is one example for this, and I'm hoping to cover more examples on this. And so let's go back and look at it one more time. So what did we do? We used De Morgan's law. So first off, we wrote out the whole entire statement, and that took us to breaking it down to its logical equivalence, which is this. And then we did the logical equivalence of De Morgan's law, which give us this new statement right here, which is right here. And it would probably been better if I rated a different color. Right here. This was logically equivalent to this. So that was a whole new statement. A whole new statement that's the same. And then we did the logical equivalence of the inequalities for that. So what's the first thing we need to do? We need to establish what our statements are, right? Jim is tall is one statement, and Jim is thin is one statement. And so these are our statements, components, etc. And we need to establish our symbol, so that's our symbol. So we're going to negate this statement. And so if you remember what we need to do, we need to put it into parentheses. We negate it. It's logically equivalent to our next following statement, which is going to be negation P or negation Q. And this is De Morgan's law. So what are we going to do now, since we flipped it? Well, we're going to have to change how our English statement said. So we got to say Jim is not tall, or Jim is not thin. So that would be our answer. But there's always another idea. This could sound a little confusing in English, right? Jim is not tall or Jim is not thin. So we're going to have to rephrase this. So we're going to have it say Jim is not tall and thin, period. And these should have periods too. And so now we figure it out. That's the end of it. But I know you guys have a lot of questions, right? How do we go from Jim is tall and Jim is thin to Jim is not tall or Jim is not thin to Jim is not tall and thin? Well, we know the step that went through here. We used the logical equivalence of De Morgan's law. And now we rephrase it like this, which we're going to explain right now. This is logically equivalent to that. So the question we're posing right now, does this violate De Morgan's law? Well, it does not. And why is that? The reason is that in formal logic, the words and or are allowed only between complete statements. And so we know back in English classes, we know this is not a complete statement. And so let's carry on to what else we need to know about this. So and or are allowed only between complete statements, not between sentence fragments. And if you remember when you're a little kid, when you're a little kid, you would probably write stuff like this. You're like, my dad is tall and my dad is smart and my dad is this and my dad is that and my dad does this, or etc., and so forth. We could use other examples. And what do we got to teach those kids? We got to teach them how to properly put coherent sentences together. And so this is just the same concept. We can't just go from one form and have it not make sense. So we got to go from one form that, and so we could actually, when you get better at this, we could skip this step. But for now, we're going to go through this step to go to this step, which makes sense in English. And so what do we need to learn from this example? Well, first thing we need to learn is that we must have complete statements on either side of each and or, and on either side of each other. So each or. So basically what that was saying is you just need complete statements no matter what. If I was writing in an English class, if I was writing a proof, if I was doing anything, it needs to be easily understandable for whoever's reading it. And so that's what it's just posing on us. That's the big question. And so I hope you understand what's going on. But that's a big idea from this. So let's go on to our next thing. Tautologies and contradictions. So we're going to define these two new terms. And all they really mean is truth and false. Truth and false. So, and we'll explain that in a bit. Let's define them first. So our first definition says, a tautology is a statement form that is always true regarding of the truth values of the individual statements, substituted for its statement variables. And so, what are our statement variables? And so I hope I've been teaching you well, because I've been emphasizing a lot of this stuff. And so that's what I want you to learn is our statement variables were P and Q. Also our component forms, R, etc. And so forth. These dots, remember? If you remember in set, in our language of sets, that means and so forth. And so on in the informal sense. A statement whose form is a tautology is a tautological statement. And so I've said that's what we say if a statement is a tautology. And so this is just a way of phrasing of saying something, right? And I'll say it when it comes up. I'll say that's a tautological statement. And so we don't have to worry about that yet. We just need to know that a tautology is a statement that is always true regarding of the truth values of the individual statement, substitute for a statement variable. And so if we had a truth table, it's going to say P, and then it's going to be substituted for one of these. Let's say for Q, right? And it's going to have its own way it's formed. And so a tautology is given with the lowercase t. That's going to be the symbol for tautology. And so let's make a little truth table really quick. it's not going to have any statements over here or full sentences. Remember, we have true and false. For if we have a 2 to the power of 1 statement variables. And so all that means for t, everything down is going to be true. So it's going to be true, true. And let's say we had a 10 statement variables, all the way down going from the columns, it's all going to be true. So let's say I have like lowercase t, so I'll put it like this in this form, so you could tell it's going to look like that. So it's going to be, say, all the way down from my truth table, it's going to say true, 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 and so forth. 3 little dots mean what they mean? So forth, and so forth. So right here we're going to have a contradiction. That's our next big thing. A contradiction is a statement form that is always false regardless of the truth values of the individual statement. Substitute for it its statement variable. And just like earlier, we remember what our statement variables are. They're going to be p, q's, and r's. And that's our components for our statements. And so let's say we substitute for q. And we're going to have a truth table. And it's going to say p in lowercase c. So when we're writing truth tables, make sure you always never really take this t's and c's. But I want you to see the symbol better. The symbol looks kind of like this. So if you write a t, write it out like that. And know that this is going to be your tautology, right? This is your statement variable for tautology. And this is your statement variable for a contradiction. And so I'm going to put this truth table. And if you guessed it, it's going to be false, false, right? And just like this, if we have a contradiction, then I have a truth table, it's going to be false, 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 and so forth. And so that defines a contradiction. And right here it says a statement whose form is a contradictory statement. And so a contradictory statement is just one that contains the C. And we'll explain it in a few. Alright, so our example right here says tautology and contradictions. And so we're going to show that the statement from P, and that's supposed to be or negation P is a tautology, and the statement from P and negation P is a contradiction. And these are going to be our steps. So first step, right? Just making a truth table like always. We're going to have P. And so we know we only have a statement for the power of 2 over 1. And so that's going to be true, false. And so what's our next following thing we need to know? We have a negation P, so we need to identify what our is not P stands for. So that's going to be false and true. And so now we have two separate compound statements, right? These are compound statements. Two separate compound statements that we need to formulate into this truth table. And so the first question that was posed on us is show the statements from P to or negation P is a tautology. And so let's do that one first. That's supposed to be a negation. I don't think I ever mentioned that sometimes instead of making a squiggly line, sometimes you just put a little dash line. And that little dash line stands for the same thing, is not. And for me, most of the time, I'm going to put this sign, okay? So don't get confused. I probably should have mentioned it a couple videos ago, but oh well. Let's carry on to this. So we're going to look at this, and then we're going to examine this. And so this says either or. So this is going to be both true. And what do we know about when the statement's all true? We just learned about it. We had this little symbol, and what is that symbol called? A tautology. So this is a tautological statement. And we just defined our statement, right? This is not just a compound statement, it's also a tautological statement. And so the only reason I say it like that, because I want you to get used to these ideas. So let's put it over here. Put it up there actually, just so you guys see. A tautological statement. And I'll put it in a different color. Put it in green. And now we're going to do this next one. It says P and negation P. P and is not P. That says true false, that obviously has to be false. That says false true, so it obviously has to be false, right? Because if one is not true, if both aren't true, then this statement is compound statement is going to be false for n's. And so what does that give us? It gives us a contradictory statement, and we're going to have this symbol that stands for C. That's what this means. Here's our example. It says logical equivalence involving tautologies and contradictions. And so this is similar to our first example, except a little different. It says if T is a tautology and C is a contradiction, show that P and T is logically equivalent to P, and P and C is logically equivalent to C. And so let's make a truth table for it. So first thing we need to do is put P, right? Because P is our initial statement, initial component, and then last thing we call this is the statement variable. So right here we're going to have true and false, and that's all this is asking right now. So what's the next thing it's saying? We never used these before, so we're going to use them. It's the first time we use this symbol in terms of a truth table. This is our tautology, and if you remember what I said, these are all going to be true. And so what are we trying to prove? And so this is a proof, and I'll explain right now. So what's happening here? Well, if we put this over here on this truth table, it's going to say P and T, or I'll put the T like that, right? And so what do we got to do? We have to check if this is true. So is it true? It says true and false, right? If P and T are true, then this is going to be true. If F and T are given right here for n, this is going to be false. And so is that logically equivalent to this? So I'll put that. Is that logically equivalent to P, which is true and false? Yes, it has the same truth values for P and T. And so we're right here. We say thus P and T are logically equivalent to P. And that's going to be our answer. But we have one more question. What's the last question it's asking? So let's move over here. Our last question was saying a contradiction. And so what's a contradiction going to be? It's going to be false, false, false all the way down. And our statement, compound statement, which says P and C. What's that going to be? So let's say we have P over here and C. P with any false statement is going to be false, right? Because it's an end statement. So you just gotta follow the logic. And so what is it asking us? It says right here, if this is logically equivalent. And we'll prove them both ways. So don't get confused right now. Remember, we have the commutative property or commutative law in this aspect. But let's focus on this right now. So if this is both false, then we prove that this is logically equivalent. This part. I use green. So all we have to say is thus P and C are logically equivalent to each other. And so that says thus the statement variable P and the statement variable C are logically equivalent to the statement variable C. And that's how you read it in the English sense. This is how you read it in the common form, more symbolic sense. So that's going to be our answer. And so like I've been saying these past couple of videos, prove all these logical equivalent statements. And so these are logical equivalent statements that you should take down as notes.